Hey everyone, welcome to section 9.7. In this section we're going to be graphing quadratic functions from a slightly different perspective than we were in the previous video. So previously we looked at the kind of salient features of a parabola, like the axis of symmetry, the vertex, the x and y intercepts. So what we are going to do in this video is look at the original, so to speak, quadratic function, x squared, and we're going to look at how various transformations affect its graph, and that's a way of graphing using transformations. So to start off with, let's compare graphs of three different functions: x squared minus 2, and x squared plus 2. And you can graph these the same way that you normally do if you plot a bunch of points. Of course, we're already fairly familiar with what the graph of f of x looks like. Now notice in the equations for g of x and h of x, they're really the same as f of x, except with that minus 2 or plus 2. So what does that mean? Well, it means when you go and plug in an x value for f of x, you're either going to subtract 2 in the case of g of x, or you're going to add 2 in the case of h of x. And remember that plugging in an x value gives you a y value. So in the case of g of x, the net result is that your points are going to be moved down 2 units from the original graph. And in the case of h of x, your points on the graph are going to be shifted up 2 units. So adding a number to x squared gives you a shift in the upwards or downwards direction. All right, now if we have the graph of x squared and we add k to it, then it just moves the graph vertically by k units. So if k is positive, the parabola is shifted upwards k units. And if k is less than 0, then the parabola is shifted downwards absolute value of k units. These are really the same pictures except for the direction in which the graph has been shifted. So it's not too bad. So let's look at another way we could transform our original graph. So we return to some more examples, f of x being the basic x squared graph that we know and love. We look here at g of x and h of x, where you're still adding or subtracting a number, except this time you do it before the number is squared. Right? According to PEMDAS, you do the expressions inside the parentheses first. So what happens when you add or subtract before squaring the number? How does that affect things? Well, if you think about it, so let's look at what we're doing. X minus 5 means that your x value is going to be 5 less than whatever it was. And that affects things in kind of the opposite way that the vertical shift does. So say we wanted to calculate g of 2, for example. So let's circle the x value that we're plugging into g of x. But the y value that we get is the square of negative 3, which is the same height as when you plug negative 3 into the original function of x squared. So we're taking that value and we're moving it over to 2. Right? And if we look at g of 5, then g of 5 here would have the same x value as f of x equals x squared at 0, which means we're taking that value and moving it over there. So the net effect here is that I am taking all the points on the graph of x squared and I'm moving them to the right by 5 units. So it's a little confusing because you usually associate minus with moving left, but it's kind of like you would have to move left 5 units from the graph in yellow to get back to the original one. That's kind of how you want to think about it. So it's the same deal for h of x. If you have a plus 5, you're instead moving in the other direction. So the graph of f of x equals x minus h is the graph of f of x equals x squared shifted horizontally by h units. If h is positive, then the parabola is shifted to the right by h units. We do want to be cognizant of the signs here, right? We're subtracting a positive number, then the parabola is shifted to the right by h units. Whereas if we're subtracting a negative number, we get x plus absolute value of h, and so the net effect is that the parabola is shifted to the left by absolute value of h units. So this is kind of opposite from the vertical, but it's explainable in that the transformed graph has to go left h units in the case of h being positive, or the transformed graph has to go to the right absolute value of h units to get back to the original. So here we want to just make the call whether or not each parabola has been shifted to the left or to the right. X plus 1 we really want to write as x minus negative 1. So we see that we're subtracting a negative number, which means according to what we just talked about, this graph is moved to the left 1 unit. But over here, we're subtracting a positive number. So this second function has been shifted to the right by 3 units. Then we get to this third guy. You might be tempted to say, oh, well, then we shift to right 8 units. But if you look at the other two, you see a key difference is that this 8 is coming after the x has been squared, which really means that this parabola has not been shifted left or right, but it's been shifted down 8 units. So there is no horizontal shift. This is a trick question, I guess. All right, the next kind of transformation we'll look at is changing the coefficient of x squared. So again, we have our basic x squared graph, nothing terribly unusual about that. If we look at the equation for g of x, then I'm going to be taking whatever value I get on the graph of f of x, and I'm going to be doubling it. So here at 1, for example, where the height is 1, my new height would be 2. And here at a height of 4, my new height would be 8. And the same thing happens on the negative side. So depending on where you are in the parabola, you're going to be moving up or down more. And so actually the net effect is that the parabola gets skinnier looking. Because it's almost like we're taking this, we grab a hold of the green parabola and we stretch it vertically. And that makes the parabola look skinnier. We can do the same thing but with a half, except now instead of the points moving upwards, they're going to be moving downwards by half of whatever their value is. So, I know 4 squared is 16, but on h of x, if I half that y value, I would get 8. So that has the opposite effect of multiplying by 2. That is, it widens the graph of f of x by a factor of 2. So the graph of f of x equals ax squared is the graph of f of x equals x squared, being either stretched or shrunk vertically by a factor of absolute value of a. As far as the sign is concerned, that really just influences whether the parabola opens up or down. What matters is the size of a, that is the absolute value. So if a is between 0 and 1, which we saw in the case where we looked at a half x squared, the graph is going to be widened by a factor of a. If a is greater than 1 in absolute value, then the graph is narrowed by a factor of a. So both of those curves in white are the same curve, and then the yellow curve is the transformed version. So now that we know all of how the transformations affect the graph of our quadratic functions, you might be asking yourself, well, okay, not every equation looks like that. So how can I figure out how to graph? Well, basically, what you do is rewrite your quadratic function like this. A times x minus h quantity squared plus k, and you do it by completing the square. And once you have it in that form, which is really the bulk of the work, then you can figure out how to graph it by knowing what the stretch or shrink factor is, the horizontal shift, and the vertical shift. So let's look at an example. Here we have f of x equals negative 2x squared minus 4x plus 2. All right, so we want to get this in the form a times x minus h squared plus k. First thing that I'm going to want to do is factor out this negative 2, make my life a little bit easier. And once you've done that, you see right away that the stuff inside of the parentheses factors as the perfect square of x plus 1. So let's graph that. So now we're just going to analyze. We have a plus 1 inside of the squared expression. So this means that my parabola has been shifted. This guy's been shifted left 1 unit. It doesn't have a plus or minus k after the square, so no vertical shift. It opens downwards because the thing that we're multiplying by is negative. And it's going to be narrowed. Because 2 is greater than 1. All right, I shift it left 1 unit, so that means my vertex is going to be, instead of 0, 0, it's going to be at negative 1, 0. And it's going to be opening downwards. So after squaring it, you're just doubling the y value, right? So when I square 1, and then double the y value, I get 2, and then square 2, I get 4, double that again, we get 8, and so the result that we end up with is this guy. And there we have our transformed parabola. Alright, so this wraps it up for Chapter 9. We've got a little bit left to go yet. We're just going to cover a few sections of Chapter 10 on exponential and logarithmic functions, which are actually fairly important as far as applications are concerned. We're not going to dive too deeply into anything, but it's still important that we go over it. So, look forward to that.